Iterative solution and convergence of nonlinear Volterra integral equations of the second kind. Using HPM. An iterative method is developed to solve a class of nonlinear Volterra integral equations. This method uses the concept of homotopy perturbation to approximate the exact solution of the integral equation. The convergence is discussed and illustrated with examples. Examples are used to show the validity of the algorithm and theorems presented, which shows that the method is effective and easy to implement. Keywords: homotopy perturbation method, nonlinear Volterra integral, convergence, numerical method. Subject class, numerical method. 1. Introduction. Solution to integral equations is of high interest in science, since these equations appear in many applied problems, which in many cases takes the form of the so-called Fredholm or Volterra integral equations. These equations result from direct model or from solving another problem like the one encountered by Chika and Hushiar 5. The_IJERT methods have been developed to solve these integral equations, some which are presented in 1. These methods have some assumptions like requiring separable kernel linearity, etc. Hence, there is need to develop more methods that will solve the_IJERT classes of these equations. Homotopy perturbation method, HPM, has been good in solving nonlinear equations ever since it was introduced by He. 7. And this has been applied to solve linear integral equations like the one by Abbas-Bandi 8. The convergence of this method has been studied as well, like the ones presented in 4 and 6. J. Bayazar and H. Gajvani too used this method to solve nonlinear Fredholm integral, which worked well. The aim of this work is to apply this method in nonlinear Volterra integral and study its convergence. Numerical, or iterative, algorithm developed using homotopy perturbation as well as examples showing the validity of the algorithm is presented in Section 2. Section 3 discusses the convergence and Section 4 has the conclusion and future works. 2. Numerical algorithm and examples. Let's consider the nonlinear Volterra integral equation. Conclusion. The algorithm developed using homotopy perturbation method performs well as shown in the examples. The percentage error in the shown examples are all less than 0.65% except in example 3, which has up to 2.65%. This is explained by the convergence theorems. Since fourth partial sum is used in all the computations, better approximation can be gotten by adding more terms. This algorithm is easy to implement and gives good approximation. Given the impressive performance, future communication will involve more analysis and extending the method to more general class of nonlinear Volterra integral.